Lewis law constant for dinitrogen in water is 3.8 times 10 to negative 4 moles per atmospheric pressure. First thing we need to do is calculate the molarity of dinitrogen in blood that is in contact with air at 1 atmospheric pressure. So we're going to use our partial pressure formula, which is C equals Kp. And then we're going to use 78% nitrogen in air, because that's what we kind of calculate it as. So we're going to turn that into atmospheric pressures first to be able to plug it into our formula. So for each 1 atmospheric pressure, we know that there is 0.075% of nitrogen in oxygen. Throw the unit you don't want on the bottom. That gives us 0.78 atmospheric pressures nitrogen. And now we can plug it into our formula, which is C equals Henry's constant, which is 3.8 times 10 to the negative 4th. Then we're going to times it by our nitrogen, 0.78 atmospheric pressures of nitrogen. That gives us 2.964 times 10 to the negative 4th moles of nitrogen per 1 atmospheric pressure. Nitrogen. Now we need to calculate the molarity of dinitrogen in blood that is in contact with air at 4 atmospheric pressures. We're going to do the same thing, but this time we're going to times it by 4. So 4 atmospheric pressures. We know that for every 1 atmospheric pressure, there is 0.78 molecules of nitrogen. That's going to give us 11.856 times 10 to the negative 4th moles of nitrogen at 4 atmospheric pressures. Now we need to calculate the volume of dinitrogen that will be released from 5 liters of blood if the deep sea diver rapidly ascends to the surface and the air goes from 4 to 1 atmospheric pressure. So we're going to minus 11.856 times 10 to the 4th. This is at 4 atmospheric pressures. And we're going to minus our 2.964 times 10 to the negative 4th. Minus that. And we get 0.000892 moles. Now we're going to use our conversion factor right here. So in every liter, that means we have 0.000892 moles of nitrogen over 1 liter. We're going to times that by 5, not only because it's given, but that's about how much blood there is in a human is 5 liters. That then you get 0.00446 moles of nitrogen. Now we're going to use our ideal gas law, which is PV equals nRT. But since we are looking for volume, we're going to divide this P out. We're going to divide that P out. So we're really using V equals nRT. There it is. So we're going to plug that in. And that's going to be 0.0044 0.046. These are moles of nitrogen. Now we're going to put 0.08206, which is our constant. And then our temperature, which is given, is 310 Kelvin. All that over 1 atmospheric pressure, because that is where we are ending at. So we have 0.113 liters of nitrogen that's being released. And finally, it says, if the escape happens in the form of bubbles of 1 milliliter diameter, how many bubbles per liter of blood is this? So we need the volume of sphere formula, which is our 4 divided by 3 pi cubed r. So we're going to put this up here, and then we're going to convert because it gave us in milliliters, and we need centimeters to be able to use this formula. So we're going to do 1 milliliter, and for every 1 milliliter, we have 10. We have 1 centimeters. That gives us 1 centimeter in diameter. We're going to divide that by 2, which equals 0.05 centimeters in our radius. Now we can plug it in. So our volume equals 4 divided by 3 pi 0.05. Cube that. So 1 bubble, the big number, 5.236 times 10 to the negative 4 centimeters cubed. This is the volume of 1 bubble. Now we're going to convert this to liters. So we're going to put 1 milliliter, 1 cubic centimeter. And there is 1,000 milliliters in 1 liter. Okay, so we have 5.236 times 10 to the negative 7 liters. Okay, so now that we have our 1 bubble, we are going to 0.113 liters. So for every 5.236 liters, that equals 215,814.28 bubbles. We're going to divide that by 5, or 5 liters. So that means we get 43162 82056 bubbles per liter. And there it is.